Okay, in this video we are just going to solve this integral. So it's the integral of the natural log of the quantity radical x plus 1 dx. So that's our goal. We're going to solve this. So to begin with, this looks like something I have no idea how to do, and usually when that's the case, it's actually an integration by parts problem. So it's the kind of integration by parts where you just let dv equal dx and hope for the best. So we're going to use integration by parts and see what happens. So I'm going to let u equal this natural log thing. So natural log of radical x plus 1. And then dv is just dx. So du is going to be kind of gross. So it's 1 over the thing times the derivative of the thing. So du is 1 over the thing. And then the derivative of the thing, so it's the derivative of radical x is 1/2 x to the negative 1/2, and then the derivative of this is 1/2 the quantity x plus 1 to the negative 1/2, and then dx. And then if dv is dx, then v is actually just x. So all right, let's start to do the integral. So it's going to be uv, and then minus the integral of v du. So I'm realizing here that I really need to simplify my du if this is going to work out. So let's go and do that. So this is some, let's create a complex fraction. So we have this, and then what I'm going to get a common denominator in the numerator. So that's going to be just root x plus 1 plus root x over 2 root x plus 1. That's still all over root x plus 1. But that's actually kind of nice because we can rearrange this. So I'm going to change it to the top fraction times 1 over the bottom fraction. So keep, change, turn is how I learned that. So we have this, and then we can actually cancel those. So du has simplified down to just this. And remember, we're doing that because we want to actually do the integral of v du. So at this point, we're back up here to our integration by parts. So we have x, natural log of root x plus 1, minus the integral of v du gives us x dx over 2 root x plus 1. Okay, so far so good. So I'm going to copy some stuff over to a new page. This is what we have so far. I think it's probably better if we take that 1/2 out of the integral. So I'm actually just going to rewrite the whole thing, but you can see that integral at the end there I've taken 1/2 out of. All right, and I'm going to call this number 1 because we're going to come back to this, and we're going to evaluate this integral at the end here and do a lot of substitution. So our goal now is just to do that integral. So we want to do the integral of x over root x plus 1 dx. This to me looks like a substitution problem, so I'm going to try that. So I'm going to let u equal radical x, and that means that u squared is x, and I'm going to make a substitution for that because I see an x in my integrand. And then based on that, I know that 2u du is equal to dx, and I obviously have to substitute that. And then we're going to return to the fact that u is equal to radical x eventually. Eventually we have to get rid of all of our u's, right? So let's make a special note of that. And let's do the substitutions now. So our integral, so it's the integral of x dx over root x plus 1. We're going to change that entirely into an integral in terms of u. So it becomes x is u squared, and then over radical x is u, that was our choice. Radical x plus 1, so x is u squared, so that'll become radical u squared plus 1. And then dx is 2u du. Okay, so far not terrible. Let's rewrite this because so we have a 2u in the numerator and a u in the denominator, so we can cancel that. I'm going to take the 2 out of the integral. So we're doing 2, the integral of just u squared over radical u squared plus 1 du. So this integral I kind of feel like it looks like a substitution, so I'm actually just going to try a substitution and see what happens. So I would let w equal the radical in the denominator, which means w squared is u squared plus, w squared minus 1 is u squared, right? Square both sides, subtract 1, so we get that. But then when I find, I need to substitute for du, so 2w dw is 2u du. So if you look at the original integrand, in the denominator I'll just get w based on my substitutions. In the numerator I'll have u squared is w squared minus 1. But then the problem is du has another u with it, and there just aren't enough u's. So substitution is not the way to go on this, so let's cross that out and think about it. So if substitution doesn't work and I don't recognize anything, it might be another integration by parts problem, but I have to be kind of careful with how I pick it, right? So like I can definitely integrate u squared. I could not actually, off the top of my head, integrate 1 over radical u squared plus 1. So if I let, I'm going to call it w. If I let w equal u squared, then I wouldn't be able to integrate dv. So instead, I'm going to let w just equal u, and then I'll let dv be everything left over, which is u over root u squared plus 1 du. I actually can integrate that, right? So I don't know if you do like a q substitution or something. We're running out of letters, but if you let q, let's say, be u squared plus 1, then 2u du is equal to dq, like Dairy Queen, and then we could go from there. So we can actually do this. So dw is definitely du. V is going to be, so there should be a 2 in the numerator, so it's going to be 1/2, but then when you add 1 to the exponent, maybe just on side paper work this out, but you end up with square root of, I'm going to write it as 1 plus u squared. I don't know, if it's like u squared plus 1, I tend to just rewrite those because they tend to remind me of trig things. So now I can, let's go back to our integral, we'll just rewrite it. So our goal was 2 times the integral of u squared over radical u squared plus 1 du. We're handling that with integration by parts. So that 2 that's in front there is still there, so it's 2, the quantity. So u was being used already, so we change it to w. So it's going to be w times v, and then minus the integral of v dw. So we'll get radical 1 plus u squared du. Okay. So let's think about what we're doing at this point, right? So we're trying to do this integral, and so far we've gotten to this point. We're now dealing with that integral at the end, right? So we're really dealing with this, the integral of x over root x plus 1 dx. So far we figured out that is equal to the quantity u blah blah 2 times the quantity u root 1 plus u squared minus the integral of root 1 plus u squared du. Okay, and that is true when u is equal to root x. So what I'm going to do is I'm going to rewrite what I labeled as number 1 up there. I'm just going to rewrite it at this point, doing everything that we know so far. So our integral, this is what we're trying to find. And so far, we use integration by parts once to get to that original uv minus the integral of v du. And then the integral that we got there, we actually have ended up doing a substitution and integration by parts. So this is the integral, and we figured out that it was this, and we know that it's that when u is equal to radical x. So I'm going to substitute here. So it's 2, the quantity. I know that u is radical x, and then it'll be radical 1 plus x, because u squared is x. I'm going to leave the other part in terms of u, so minus the integral of radical 1 plus u squared du. Okay, so that I'm going to copy over to the next page, and we're going to go from here. Okay, so this, I'm actually going to simplify this a little bit, so I'm not going to make you watch. I'm just going to distribute the negative 1/2. And yeah, so I'm going to distribute the negative 1/2 because I've -1/2, and then times 2 times the quantity. So the -1/2 and the 2 are just going to cancel. So we'll get this. So notice the at the end of that first line there, it was minus the integral. It became plus the integral because it was -1/2 times 2 times -1 is +1. Okay, and then we also know that u is equal to radical x eventually. So now our goal is to do this integral at the end. So like we keep just trying to do the integral that's at the end of the line. So this, to me, looks like a trig substitution problem. So at this point, you kind of run into, like, it depends on how many things you've memorized in your life. I have not memorized this, so I'm going to draw a triangle. If I have radical 1 plus u squared, that should be the hypotenuse of the triangle. So I'm going to do that. And then I like to put u on the vertical, so I'm going to put u here, and that means that 1 would have to go here. And that's a right triangle, it satisfies it, right? So if the legs are 1 and u, then the hypotenuse would be radical 1 plus u squared. So I'm going to put a theta here, and based on the triangle, I'm going to find some substitutions. So I want a trig function that uses theta and radical 1 plus u squared, but doesn't use the other thing. So I want to use the hypotenuse, I want to use theta, and I want to use the adjacent side. So cosine could work, but that would put it in the radical in the denominator, so I'm going to use secant. So secant of theta is radical 1 plus u squared. Now I want, somehow I need to substitute for du. So I'd like to write a trig function that uses just u, not the radical thing. So a trig function that uses just u, tangent will do that, right? Tangent of theta is u over 1. So I'm going to say tan of theta is u. And then I can use that to find du. So the derivative of tangent is secant squared of theta, d theta, is du. Okay, so I can use this to make substitutions in the original integral, which is far from the original integral, but the integral of radical 1 plus u squared. Okay, so radical 1 plus u squared we said was secant of theta. Du we said was secant squared of theta d theta. Okay, so this is just secant cubed. So I have memorized the antiderivative of secant cubed. If you've done that, you're basically done with the problem at this point, but if you haven't done that, now we need to figure out the integral of secant cubed, which is not exactly a trivial problem. So I'm going to run through that, but if you already know it, you're basically done with the problem. You just make the substitution, make a lot of substitutions, and then simplify. But we're going to keep going. We're going to assume that you don't know the integral of secant cubed. So this is another one we can do by integration by parts. I'm going to let u equal secant. I'm going to let dv equal secant squared d theta. Secant squared of theta d theta. Okay, so that means that du is secant theta tan theta, and then d theta. And v is just tan of theta. Okay, so our integral of secant cubed is going to be, so it's uv, so secant tan, minus the integral of secant times tangent squared, because it's v du, which is secant tan times tan. So the integral of secant times tan squared. Now you have to remember what to do with secant times tan squared. So what I'm going to do is I'm going to replace tan squared, but I have to remember a Pythagorean identity to do it. I know that 1 plus tan squared is equal to secant squared, so I can make that substitution. So let's do that. Okay. It's actually, even if you have memorized the antiderivative of secant cubed, it's a good idea to go through this every once in a while because it's like there's a lot of good skills in here. So I'm replacing tan squared with with secant squared minus 1, I should say, and then distributing the secant. So I get this point, right? So secant times tan squared becomes secant cubed minus secant. But look at that. So we have a minus the integral of secant cubed. That's the original integral. I'll be able to move that to the other side. So let me just rewrite this. I'm going to distribute that negative sign. It's always hard to decide how much work to show in these things. It's like if you've gotten to the point where in your life where you're trying to do this integral, you can probably follow a lot of these steps without me showing them, but I feel like I should show them anyway. You can always speed this up or skip it. Okay, so we're at this point. I'm going to add that over, and I end up at this point. So 2 secant cubed d theta is secant theta, tan theta, and then plus the integral of secant theta d theta. Okay, I'm going to copy over all of the relevant stuff to the next page. Hopefully you're following along so you just like have it with you, but I'm probably going to need it. So I'm copying all the relevant stuff, which is a lot of stuff. So we have our integral that we're trying to do. We've gotten to a certain point. We're trying to do the integral of radical 1 plus u squared. We turned it into the integral of secant cubed. We have our triangle, which is like a dictionary of terms that will allow us to change from trig functions into things that are in terms of u. And then we know that u will be radical x like at the end. Okay, now our goal is, remember we're basically always trying to do the integral at the end of a line. So we need to do the integral of secant. So the integral of secant, if you remember it, you're lucky. If you don't, you have to kind of remember this technique. We multiply by a very weird form of 1, and that form of 1 is secant plus tan over secant plus tan. And we're doing that for a very specific reason. The reason is it works. People always wonder, like, who came up with this? I feel like it was probably someone taking the derivative of the thing we're going to get. But who knows? Maybe somebody like Euler thought of a lot of things. And this seems like it's kind of sub-Euler level. Like, not really. You don't really need to be Euler to work this out, but you need to be good at trig stuff. So I'm just distributing here. And then if you look at it, if I let u equal the denominator, right, u is equal to secant plus tan, the derivative of secant is secant tan, the derivative of tangent is secant squared. This is a perfect natural log. So the integral of secant, is that left-hand thing, is actually just the natural log of the absolute value of secant theta plus tan theta. So we now know that going back up, because we're doing the integral of secant cubed, remember, and we so far at 2 times the integral of secant cubed is secant tan plus the integral of secant. So let's substitute again. So we're subbing this. So 2 integral of secant cubed is secant times tangent, and then plus the natural log, the absolute value of secant plus tangent, technically plus c, but we're saving that for the end because like we're accumulating a lot of c's here that we'll just combine. So we found that the integral of secant cubed is 1/2 secant tan plus the natural log of absolute value of secant plus tan. The way that I remember that is that the integral of secant cubed is the average of the derivative of secant and the antiderivative of secant, which means you have to remember the derivative and the antiderivative of secant, but if you can remember those, you can remember the integral of secant cubed. Secant cubed comes up way more than you would expect. All right, I'm going to copy over just like everything we have so far that's like important. So I'm trying to figure out the integral of radical 1 plus u squared, so I should probably now go from these trig functions of theta back to functions of u. And I can do that by using my triangle stuff. So radical 1 plus u squared, the integral of radical 1 plus u squared is 1/2. Secant of theta is radical 1 plus u squared, and then tan of theta is just u, plus natural log, absolute value, secant of theta again, radical 1 plus u squared, and then tangent is u, and absolute value, close, close. Okay, but we know that u is equal to radical x, so let's substitute here. So this thing, the integral of radical 1 plus u squared is 1/2 radical 1 plus x plus, times radical x plus the natural log of the absolute value, radical 1 plus x plus root x. Whew, okay. So that integral up there in that top, the second line there, we just figured out is actually this thing. So now we're like really close to done. So we're gonna substitute for that integral and we'll get something entirely in terms of x. So this is awesome. Let's copy over just everything that we have so far. Let's just rewrite it. So natural log radical x plus 1 dx. So this is pure copying. We're basically done. So, I mean, if you're happy with the way this looks, you could probably stop it there. There's a couple of things that we can still do. So we have this. All right, so that's our first look at what the answer like really looks like. Now what I'm going to do is that absolute value, the natural log of the absolute value thing, is kind of an issue. It's not a big issue, but we have minus radical x plus 1 and plus 1/2 radical x plus 1. That was like really hard to say. So I'm going to combine those. So this turned into a monster. Like, who knew going into it? Except, I mean, the title of this is just this integral, which probably makes, and then you see that it's like 20-something minutes long. You probably expect this to not be that simple. So I'm going to make this minus 1/2 root 1 plus x, or root x, root 1 plus x. I'm having a lot of trouble saying that. Okay, so if you think about it, radical 1 plus x plus radical x can never be negative. Both of those just spit out positive values. And so what's going to happen there is we don't actually need the absolute value. So I'm going to drop the absolute value. So it's going to be plus 1/2 the natural log of just root x plus 1. I've developed a real problem saying that. So we have that, but now we have like that natural log showing up twice. So we can also simplify that. So I'm going to actually like factor that out of the two things and just write it in like the final way that I'll write the answer. So I'm going to make it the quantity x plus 1/2, that natural log, radical x plus 1, and then minus 1/2 radical x plus 1, and then plus c. All right, there you go. That's like a very challenging integral. We use integration by parts a couple of times. We use substitution a couple of times. We use trig substitution, and then we had to like back solve everything or back substitute. But anyway, if you stuck it out, I hope you found this helpful, and good luck.